Eric, I'm so hungry. How about grab some food?
Okay, Eric, where do you want to go?
Let's go eat Burger King. I want to eat some burger.
What about Sonic? It's like really cool burger.
We have cars right now. We can just drive through and get some food really fast.
Oh, have you ever tried Sonic before? You could like drive in and order food, so it's like really cool. It's like from where I was from. I had 1 year in Oklahoma.
So what is different between the drive-through and the true restaurant?
So, like in Sonic, you could literally just drive in their parking lot and order there, and they'll like just grab your food to you. So it's really cool if you want to try that.
Oh, it sounds really cool. So how about just go there?
So here we have arrived at Sonic. So you could basically just grab food wherever you park, and we're going to check out the drive-through line. So here's the drive-through line. It's kind of busy today, so we are going to just park somewhere and get some food.
Look, Eric, so many kinds of food. Hi, can we just get a Sprite Zero for medium, please?
A medium Sprite Zero?
Yes. Okay, thank you. Thank you so much.
No problem. I lost your straw. The wind took it away from me, so
Oh,
I'm going to
really?
get you another one.
It's alright, actually.
You don't want the straw?
Yeah, it's alright.
Okay.
Thank you so much.
All right, have a good day.
See, Eric, it's really fast and really cool.
Welcome to our IE413 project. We will introduce our simulation model in the following video. In this project, we will model the customer service system at a fast food chain restaurant called Sonic, which originated in Oklahoma. At Sonic, customers arriving at the restaurant can be served in two ways, either in a drive-in manner, in which they will park their cars in the restaurant's parking slots and wait until their food delivered by server to them, or in a traditional drive-through manner, which most of us have seen in other restaurants, such as Burger King. A customer can drive through the restaurant and order food at the vehicle queue. It is known that many restaurants that have drive-in or drive-through service will prioritize some customers in order to maintain a smooth customer experience. In this project, we will use a modified version of non-preemptive priority queue as a model to simulate the customer service system in the restaurant. We will then analyze the performance of the system based on the statistic output of the simulation model. To better construct a simulation model, we made a few assumptions. First, we assume that the arrival rate of customers, both drive-through and drive-in customers, will follow a non-homogeneous Poisson distribution, in which the rate of the Poisson distribution may vary at a different time within the day. The reason of doing so is to approximate the reality as much as possible. Moreover, customers in both queues will choose to leave the restaurant if the queue is already full.
Here are several of the default parameters of our model. First, we assume that the operation hours at Sonic's ranges from 6 a.m. to 12 a.m. Second, we assume that all of the drive-through customers will have higher priorities than drive-in customers. Third, we assume that all queues will have a maximum capacity of 10. Fourth, we assume that there will be 10 chefs during busy hours and 5 chefs during non-busy hours. Finally, we assume that each chef will have a serving rate distributed uniformly from 30 seconds to 2 minutes. Our model includes the following entities: customers in two different types, either drive-through or drive-in; ordering servers, the people who process incoming order information and pass them to the chefs; two ordering queues and two serving queues for different types of customers. The serving queues are the ones used by the chef internally when they are preparing for the food. Also, the most important component, the chefs themselves. Every time a new customer arrives, the arrival event will be triggered. After that, the customer can choose to either leave the restaurant if there are too many people already at the restaurant and there are no available parking slots. Otherwise, the customer will choose to order for the food. After the customer finishes ordering, the e-order event will be triggered. Then, depending on the type of the customer may be put into the drive-through customer serving queue, indicated by the event V located at the bottom, or the drive-in customer serving queue, indicated by the event in queue P located at the top. The begin service event indicates the time when the chef starts to prepare food for the customer, and the end service event indicates the time when the customer actually received the food. At 12 a.m., the restaurant will close and the close event will be triggered. The close event will cancel all of the scheduled arrival event and immediately schedule two other events called F-leave V and F-leave P. These two events will remove the customers one by one until all of the queues are empty. After 1 hour, which is at 1 a.m., the restaurant will reopen and continue to accept new arrival. We propose a 3-part Poisson distribution for customer arrival. Plot is an actual customer arrival data collected from another fast food chain restaurant. You can see that the rate of customer arrival varies drastically during early morning, daytime, and nighttime. Therefore, it shows that our 3-part Poisson distribution is very likely to be a valid candidate to model the real-world distribution of customer arrival. Later, we perform a chi-square test, which verifies that our proposed arrival distribution indeed match very closely to the actual arrival distribution. Here are several of the results produced by our simulation model. First, we notice that the number of customer arrival per day is around 2,000, while the number of customers left without being served per day is only around 250. This means that our default model is quite successful because the number of customers left without being served each day is relatively low compared to the total number of customer arrival. Since we are using a non-homogeneous Poisson process to simulate customer arrival, we also observed that there are some obvious periodic waving patterns in the total queue length and the waiting time, with the waiting time and the queue length being negatively correlated. We compared the distribution of number of customers in the queue and the distribution of waiting times between the drive-through customer and the drive-in customers. We observed that the queue size and waiting times are generally longer for drive-in customers than drive-through customers, which is a reasonable observation since the restaurant prioritized drive-through customer over drive-in customers. We also compared the distribution of queue size and waiting time during day and night. We noticed that both measurements are significantly lower during night than during days, which matches with our collected real-world data. Besides doing statistical analysis on various outputs from the model, we have also tried to optimize the model by changing a subset of parameters. We observed that the number of chefs and the number of counters are two important parameters that can affect the model's performance. Therefore, we use the average customer waiting time as the performance metrics for our model and perform a grid search on the parameter space defined by those two parameters. And we found that the optimal values for those parameters are 2 counters and 8 chefs, which produce the minimum average customer waiting time. Even though our 3-part Poisson distribution passed the statistical test, we still cannot guarantee that the 3-part Poisson distribution is exactly the non-homogeneous Poisson distribution in the real-world scenario. Therefore, using our estimated Poisson distribution to model customer arrival may induce potential errors in the output of our model. We also assume that every customer will choose to immediately leave the restaurant if they find out that there are no available parking slots in the restaurant, or if the drive-through queue has been too long. However, this may not be the case since some customers may choose to leave the restaurant first and come back later after a certain period of time. And this kind of reorbiting behavior is not captured by our model. Then we assume that store will operate for 18 hours each day. However, this is not true since during weekend the store only operates for 12 hours. Further, we assume that priority is only implemented at the serving period and not during the ordering period, which means that the orders from the drive-in and drive-through customers are handled perfectly independently. And there may be exceptions to this assumption in the real-world scenarios. Finally, we assume that the serving rate of each chef is between 30 seconds to 2 minutes. However, this data is purely from our speculation, and there are no real-world data that can support such assumptions. Therefore, the serving interval of each chef may be another potential source of error.
Thank you for watching our project.
Should the fastest one.